So you see, synchronous machine can be classified into two types. First of all, number one is your wound field synchronous machine, another is a permanent magnet synchronous machine. So what is the meaning of wound field synchronous machine and what is the meaning of permanent magnet synchronous machine? So wound field means that you can expect field windings are placed over the rotor. So there will be a field winding present in case of wound field synchronous machine. So if I want to write a comment, I should write like this, that in wound field synchronous machine, field windings are present. Field windings are present. Field windings are present. Now usually it is placed on the rotor, not on the stator. For large rating synchronous machine, that is another issue. But in wound field synchronous machine, you will have field windings. But in case of your permanent magnet synchronous machine, field windings are absent. In this case, field windings are absent. Field winding is absent. So how do we set up magnetic flux in the air gap? Magnetic flux is set up in the air gap. Magnetic flux is set up in the air gap. Magnetic flux is set up in the air gap due to the presence of permanent magnet. So we are having permanent magnet placed on the rotor. So due to that only magnetic field is set up. Now regarding this wound field synchronous machine, how many types are there? Wound field synchronous machine can be classified into two types. You can see cylindrical rotor and salient pole synchronous machine. So these are the cross-sectional view. This is your cylindrical rotor type. This one is your cylindrical rotor. You can find it easily. This thing is your cylindrical rotor. This is your cylindrical rotor and this is your salient pole type rotor. This thing is your salient pole type rotor. Salient pole type rotor. So you see in salient pole type rotor the field poles are projecting out or they are sticking out from a surface. If I just draw like this, let's say this is our round shape. So you can see these poles are actually sticking out. These poles are actually sticking out from this surface. Now let me show you some of the diagrams of salient pole rotor. So this is your cylindrical rotor. This thing is your cylindrical rotor. You can make it out from the diagram. This is your cylindrical rotor. And you can see here there is a comparison right away in front of you. So this is your cylindrical rotor or non-salient pole type rotor. So this thing is your non-salient pole. Non-salient pole type synchronous machine, and this thing is your salient pole type. This thing is your salient pole. This thing is your salient pole type. This thing is your salient pole type synchronous machine. So you can see these structures are actually sticking out or protruding out. You can see these are the structures which is protruding out. So this thing is your salient pole structure. These things is your salient pole structure. Same way you can see these things are the portions which are protruding out, salient pole structure, like that, this one. The same thing goes with this one. So these things are, as you can see, they are protruding out. They are projecting out from the rotor surface, So this is your salient pole type, and this is your smooth. So this thing is also known as a cylindrical rotor or round rotor. This is also known as cylindrical rotor, cylindrical rotor, or you can also call it to be round rotor, cylindrical rotor or round rotor alternator. Now we are required to make certain conclusions between these two. What are this? This is used in thermal power station. So this kind of rotor construction, this rotor construction, this rotor construction is suitable for high speed, application. So wherever you are expecting that the operating speed is to be kept very high, so there you can use this kind of synchronous machine which is having this kind of rotor, which is your cylindrical rotor or round rotor. So you see, these three are the names of the same thing. As I have shown in the diagram, some people call this to be your non-salient pole type synchronous machine. Some people call it to be cylindrical rotor or round rotor. Now, this cylindrical rotor construction is more suitable for high speed application. So high speed application means it can be used in thermal power station. Suitable for thermal power station. So this kind of rotor construction is used for those alternators. This kind of rotor construction, this kind of rotor construction is used for those alternators, is used for alternators, This kind of rotor construction is used for alternators to be used in thermal power station. For alternators which will be used in thermal power station, which will be used in thermal power station, I will tell you why it is used in thermal power station, because in thermal power station we are using steam turbine, and efficiency of steam turbine is more if it is rotated at high speed. So that is the reason that it is for high speed application. Now this kind of rotor construction is suitable for hydroelectric application. This kind of rotor construction is suitable for low speed application, and it is used in hydropower station. This kind of rotor construction is used in hydropower construction. So we can write the same phrase, this kind of rotor construction is used for alternators in hydropower station, hydropower stations. Now, what is another point which you can see? This is a mechanically weak structure. This one you can note it. You can notice this. This thing is your. This is your mechanically weak structure. This is your mechanically weak structure. This is your mechanically weak structure, and this thing is your mechanically strong structure. Mechanically strong structure. So these are another two aspects which we can remember, is that this cylindrical rotor is mechanically strong structure, and this salient pole structure is a mechanically weak structure, you can see. So it cannot withstand higher mechanical stress, the salient pole type structure, whereas cylindrical rotor, it can withstand higher mechanical stress. So now let us come why it is used like this. So I will again take you back to that slide, or let me add one page if possible. Here, over here page is there. Now you see, we are actually finding that for synchronous generator or alternators, for synchronous generator, or alternator, so for synchronous generator or alternator, the frequency of output voltage, the frequency of output voltage developed by armature winding, developed by armature winding is given by this formula, is given by, let me write first the formula for synchronous speed, 120 F by P. So this thing implies that F equals to P multiplied by Ns divided by 120, Ns by 120. So now the frequency of output voltage developed by the alternator is given by this one. Okay, so this is the formula, Pns by 2. So frequency of output voltage of an alternator, frequency of output voltage developed by armature winding, developed by armature winding depends on two factors. What are the two factors? Number one, speed of rotor. Number one is speed of rotor. Number two, number of poles. Number two is number of poles. So these are the two things which you can see from the formula, that frequency of output voltage developed by armature winding depends on two factors, speed of rotor, and another is the number of poles. Now The point to be noted over here is that the speed of the prime mover, the speed of the prime mover, the speed of the prime mover, let us save it. So the speed of the prime mover decides the speed of the prime mover decides the rotor speed. Rotor speed in case of synchronous generator. In case of synchronous generator. Synchronous generator. We also use the word alternator for referring synchronous generator. So the word alternator and synchronous generator, they can be used synonymously. So the speed of the prime mover decides the rotor speed in case of synchronous generator or alternator. Now, who decides the speed of prime mover? If this is our line of reasoning, then our question comes that who or which which factors decide decides the speed of prime mover. Speed of prime mover. So the answer to this question, that which factors or who decides the speed of prime mover, the answer is the operating speed of prime mover, the operating speed of prime mover is decided keeping in mind at which speed operating efficiency is maximum. Operating efficiency at which speed operating efficiency is maximum. Now number one, steam turbine efficiency is maximum is better. Steam turbine efficiency is better at high speed. High speed. So in thermal power station, thermal power station, speed of prime mover. Speed of prime mover means basically the steam turbine we are talking about. The steam turbine. So in thermal power station, the speed of prime mover is towards higher end. let's say is towards higher end. Let us say 3000 rpm. 3000 rpm. So if the speed is say, fixed at 3000 rpm, then the number of poles are also fixed. I tell you why. If a synchronous machine has to work in India, then the operating frequency has to be 50 Hz. So let me mention this. In India, grid frequency is 50 Hz. Grid frequency is 50 Hz. In India, grid frequency is 50 Hz. Now you can use this formula F equals to ENS by 120. So F is how much? 50 Hz. P you want to find. What is NS? It is 3000 divided by 120. So this will let you know that P equals to 2. So the speed of the rotor is NS, that is the speed of the rotor. Let me write it here. NS is the speed of rotor. Speed of rotor is same as prime mover speed. Speed of rotor is same as prime mover speed. Prime mover speed. So for high speed application, cylindrical rotor is preferred. So that is the reason we have mentioned for high speed cylindrical rotor construction is preferred, because that is mechanically more strong. So let us write for high speed application, cylindrical rotor construction is more suitable. For high speed application, cylindrical rotor construction is more suitable. So in thermal power station we use cylindrical rotor alternator, because for high speed application cylindrical rotor construction is more suitable. So in thermal power station we use. So in thermal power station we use cylindrical rotor construction, cylindrical rotor alternative. We use cylindrical rotor construction. This is the reason we use the cylindrical rotor construction in thermal power station, because in thermal power station the speed of the prime mover, that means the steam turbine, it is very high. So thereby the speed being very high and frequency is fixed at 50 Hz, we have to make sure the number of poles are 2, and besides that, if it is to rotate at high speed, that means the cylindrical rotor construction, if it is to rotate at a very high speed, the cylindrical rotor construction is more suitable. Now in hydroelectric power plant what happens? Now in hydroelectric power plant, let me mention it here. In hydroelectric power station, in hydroelectric power station, salient pole type rotor is used. salient pole type rotor construction. Salient pole type rotor is used. Again, I can use the same set of arguments which I have mentioned earlier. Now let me just copy this portion so that you don't have to write it once again. Let me copy up to this point. So the speed of the prime mover decides the rotor speed in case of synchronous generator alternator. Now who decides, or which factor decides the speed of prime mover? The operating speed of the prime mover is decided keeping in mind at which speed operating efficiency is maximum. Operating efficiency. So now here I have to replace the word steam turbine by water turbine. This will be water turbine. So this is your water turbine is better at low speed. This is not at high speed, this will be at low speed. So this I have to correct it. This will be at low speed. So in hydro power station, this will be hydro. So I have to replace the word thermal by hydro. So in hydro, hydropower station speed of prime mover, that means water turbine. I have to replace this by water. Water turbine is towards lower end, not higher end, it will be lower end. This will be lower end. Let us say 500 RPM. Let us say 500 RPM. So from here, if you can write like this, F is your 50 Hertz, P we don't know, NS is how much? It is your 500. So from here you can calculate the number of poles. So for this number of poles is coming as 12. This will come as 12 because this 0 0 cancel, 5 1 ja 5, 5 10 ja. Yes, this 0 0 cancel, this 0 5 5 cancels. Yes, P equals to 12. So now we can understand for accommodating 12 number of poles, we have to go for that salient pole construction, salient kind of construction. Now let me add this portion also. NS is the speed of the prime mover. NS is the speed of the prime mover. So NS equals to speed of rotor is same as prime mover speed, is same as prime mover speed, is same as prime mover speed. So we can see that for accommodating large number of poles, and also let me write, salient pole construction is more suitable. Salient pole type rotor construction, salient pole type rotor construction is more convenient is more convenient from the point of view of more convenient from the point of view of view of accommodating 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 12 poles over rotor surface over rotor surface. Besides this, we can also add, besides this salient pole construction is more salient type pole construction. Besides this salient type of rotor, salient type of rotor is mechanically weak structure, is mechanically weak structure and hence suitable for low speed application, suitable for low speed application low speed application. So salient pole type rotor construction is more convenient from the point of view of accommodating 12 poles over rotor surface. Besides this, salient pole type of rotor is mechanically weak structure and hence suitable for low speed application. That means in hydropower station. Now let us have a look regarding some of the points with the rotor construction. I will show you some diagrams. So this diagram I have already shown you. Now let me show you this diagram. So you can see that we are using a slip ring and brush for establishing a contact, the electrical contact between the ends of the field winding. Let us say this is our field winding. So these field windings are placed. How they are placed, if I just show you like this. This is one field winding. You can see this field winding is moving in a concentric manner. I am tracing it over this. Then you have another field winding. Sorry, let me trace it properly. You have another this field winding. So these are the field windings which are placed over the rotor, and these field windings will be connected to slip ring and brushes. So these are the slip ring and brushes. You can have another way out here, very convenient way. This is the slip ring and brushes. Now one important point needs to be mentioned. Slip rings are mounted on shaft. They are mounted on shaft, but they are insulated from it. They are insulated from shaft. So slip rings are mounted on shaft, but they are insulated from shaft. These are the brushes. Now you can see regarding the rotor surface, this portion of the rotor is kept unslotted. If I trace it over here, this is the unslotted portion of rotor. This is the unslotted. There are no slots over here. Unslotted portion of rotor. Likewise, this bottom side also you can look up, you will have unslotted portion of rotor. Unslotted portion of rotor. So why these are kept unslotted? These are kept unslotted so that magnetic lines of flux can leave and enter. These are unslotted for entry and exit of entry and exit of magnetic lines of flux. Magnetic lines of flux. Basically, we are meaning to provide low reluctance path. Okay, this time we are trying to say to provide low reluctance path. To provide low reluctance. To provide low reluctance path. That is it. The same thing can be written over here also. Now, what about the salient pole construction? This is your salient pole construction. You can see these are your field coils. These are your field coils. Of course, this is your cross-sectional view. This thing is your cross-sectional view. This thing is your cross-sectional view. Now, what are these metallic bars? These are your damper bars. These things are your these dots are damper bars. Let me indicate it more properly. These are your damper bars. These are your damper bars. What do you see? Damper bars are short circuited. You can see damper bars are short circuited. Damper bars are short circuited. Damper bars are short circuited. Let me write in a different way. Damper bars are short circuited. So these damper bars are like squirrel cage rotor. These damper bars are like squirrel cage rotors. Short circuited at both the ends. At both the ends. So you can see these damper bars are like squirrel cage rotor. So this is also damper bars. This thing is also damper bar. This thing is also damper bar. Damper bars are short circuited at both ends. Damper bars are short circuited at both ends. At both ends. Damper bars are short circuited at both ends. So they are like squirrel cage rotor. So they are like squirrel cage rotor. Of course, minus the rotor core. Squirrel cage rotor minus the rotor core minus the rotor core. That goes without saying. We are meaning that portion only. Now, this portion is also known as pole phase. This particular portion, this thing is known as pole phase. This thing is known as pole phase. This thing is known as pole phase. Similarly, over here also you can see this portion will be termed as pole phase. Pole phase. So from this portion, most of the lines of flux are leaving and entering the rotor. So that is the reason we are calling this to be the pole phase. Now, what is the function of the damper bar? Damper bars are there to damp out any kind of rotor oscillation, and rotor oscillation will come into picture if the rotor speed deviates from synchronous speed. So the function of damper bar is to damp out rotor oscillation. The function of damper bars is to carry current and thereby develop torque and thereby develop torque so as to bring rotor back to synchronous speed. So the function of the damper bars is to carry current and thereby develop torque so as to bring rotor back to synchronous speed. Note that when rotor speed is synchronous speed, when rotor speed is synchronous speed, no EMF is induced, in the rotor, in the damper bars, So this is an important point one should keep in mind thoroughly, that when rotor speed is synchronous speed, no EMF is induced in the damper bars, because in that case relative speed between the rotating magnetic field and the damper bars is zero. So the damper bar, another function is to help in the process of starting. That is, there we can take the help of damper bars for starting of synchronous motor, because synchronous machine can be operated in two modes. One is the generating mode, another is the motoring mode. So if you are using the synchronous machine as a generator, so if it is being operated in generating mode, if the synchronous machine is being operated in generating mode, so obviously there will be a prime mover. So that prime mover can make the rotor rotate. So there is no question of problem of self-starting, because the rotor will be driven by the prime mover. Why is it so? Why the rotor will be driven by the prime mover? Because the machine is to be used as a synchronous generator, so there has to be a prime mover which will give the mechanical energy as input. So that is the reason there is no problem of starting in synchronous generating mode, because the prime mover will take care about the rotation of the rotor. The shaft of the rotor and the prime mover shaft are mechanically coupled. Yes, in case of motoring mode, when the synchronous machine is working in motoring mode, you will have the problem of self-starting. Self-starting means that at the time of starting, the developed torque will be zero. When the rotor speed is zero, developed torque is also zero. So just to overcome that starting problem, also these damper bars are also useful, because damper bars, they produce induction motor torque, and this brings the rotor somewhat near to synchronous speed but not equal to synchronous speed, near to synchronous speed, and thereby the process of magnetic locking becomes easier. So sometimes these damper bars are helpful for the self starting of synchronous motor, that is also there. So if I let me write this, damper bars are also sometimes used for damper bars. Damper bars are also used are also used for starting of synchronous motor, for starting of synchronous motor, synchronous motor. Damper bars, they act like a squirrel cage rotor of a three-phase induction motor, and they bring the rotor to somewhat near to synchronous speed at the time of starting. Now, so these were the two structures which you can see, salient pole and non-salient pole. So this thing is your cylindrical rotor. You can also call this to be your non-salient pole type. This is also non-salient pole type. Non-salient pole type. And this is a salient pole type. Now you can well expect that there will be damper bars over here, like the way I am showing. These can be the damper bars which are embedded in the pole faces, and obviously these damper bar needs to be shorted so that the current can flow through them, and this shorting of the damper bars will be there at both the ends, not at this end, at the other side also. So you can expect damper bars in the pole faces. They are embedded in the pole faces like this. So these are the damper bars. So you need to short these damper bars so that current can flow. Likewise, you can have damper bars over here also, damper bars over here. So these are basically the pole faces. This thing is the pole face. This thing is the pole face. Likewise, this portion is the pole face. This portion is the pole face. From this portion, the lines of flux are leaving and entering. If it is a north pole, lines of flux will be leaving. If it is a south pole, lines of flux will be entering. You can see here, through the south pole phase, lines of flux are entering. If I just mark it over here, you can observe lines of flux are entering. Lines of flux means magnetic lines of flux are entering through the south pole phase, are entering through the south pole phase, this south pole phase. So magnetic lines of flux are entering through this south pole phase. The same thing you can expect over here. Now let me then put up some arguments regarding the why the field winding is placed on the rotor and armature winding is placed on the stator. This is an important question which you can maybe not encounter in the exam directly, but this is an important piece of question, that why is it like that we have to place the field winding on the rotor and armature winding on the stator. It has to do mainly with the physical or the practical constraint, I mean to say that theoretically there is no binding. You can place any winding anywhere. I mean to say, you can place the field winding on the stator, armature winding on the rotor. Practically, not I am saying, I am saying theoretically, no problem in that. But from practical consideration, it has been found to be place the field winding on the rotor and armature winding on the stator. So let me mention it over here. In a synchronous machine, mainly there are two windings. So in a synchronous machine, mainly there are two windings. In a synchronous machine, there are two windings mainly. There are two windings. Two windings. What are they? Number one, field winding. Number two, armature winding. Number two is armature winding. So field winding is a low power winding. It's a low power winding, and armature winding is a high power winding. Armature winding is a high power winding. Armature winding is a high power winding. So we will also, I need to mention here that this thing is known as the pole phase. This unslotted portion, this is known as this thing is also known as the pole phase. This thing is also known as the pole phase. Pole phase. This thing is also known as pole phase. This thing is also known as pole phase. Now, damper bars are usually embedded in the pole phases. So damper bars are usually embedded damper bars are usually embedded in the pole phases. Embedded in pole phases. So what are the damper bars? This thing can be a damper bar. So likewise, you can expect damper bars over here. You can expect damper bars over here. Damper bars over here. So these damper bars are running along these pole faces like this. These damper bars are like this. They are running along the pole faces. So you can just shade it for better view, but these damper bars are there running along the pole faces, and not only that, they will be actually short circuited at both the ends. They will be short circuited at both the ends, so that they are capable of carrying current, because if they are not short circuited at both ends, in that case you cannot expect the current to flow. So that is the reason they are short circuited at both the ends. So this is one end, they will be short circuited by a metallic strip, usually from the same metal, the metal from which the damper bars are built, and also over here also they will be short circuited by a metallic strip. Okay, so these are your damper bars. So you can mention this to be your damper bars. These are your damper bars. Damper bars. Okay. Now we need to just figure it out why it is there. So you see, from physical consideration, from ease of construction and economy, these are the 2 points I will mention. From the point of view point of view. Number one, ease of construction. Ease of construction. This is one thing. Another is economy. Economy in construction. It is found to place low power winding, low power field winding, low power field winding, low power field winding on rotor and high power armature winding high power armature winding on the stator in case of large rated synchronous machine. In case of large rated synchronous machine. So these are the two things from which we are saying that it is found to place low power field winding on rotor and high power armature winding on the stator in case of large rated synchronous machine. It is found to be easier. Let me erase this. It is found to be easier to place low power field winding on the rotor and high power armature winding on the stator in case of large rated synchronous machine. So from theoretical consideration there is no binding. Let me mention this also. From theoretical consideration there is no binding. There is no binding to place field winding on rotor and armature winding on stator. Field winding on rotor and armature winding on stator So from theoretical consideration there is no binding to place field winding on rotor and armature winding on stator, but from physical consideration it is done so. So I have discussed this in detail, so I will not take up this particular point. Actually there are 7 to 8 points, so I ask you to refer to the lecture which is given by me in my lab class, online lectures of laboratory class, that is PCEE 591. PCEE 591, in one of the laboratory class I have given that. So now let me again proceed to the next topic of synchronous machine. So this is one, you can see one particular representation which you can see here. Now let me show you this particular diagram. Let me show you this particular diagram. You can see here that I have shown a schematic representation of field winding which is placed on the cylindrical rotor of a synchronous machine. So what is it I want you to notice? Let me tell you. Let me tell you what is it I want you to notice. You notice the way windings are placed around. You can see here. If I just trace it along here, let me use pink color. You can see here that current is entering through this portion. Current in, you can observe this current is entering through this portion. So since current is entering, it is shown by cross. You can see here cross is indicated. Now current is following this particular path. Now this is the overhang portion of the field winding. This is the overhang portion of the field winding. Now from the other side, it is coming out from this particular slot. Now from this particular slot, here current is coming out of the screen, means it is dot. Again from here it is going inside. Again here it is cross. Again from this side it is going to the other side of the rotor, and from other side it is coming out. So in this way you can see that the current trajectory is shown or plotted like this. So you see in what way the field windings are placed over the rotor structure. Now from here, dot means current is coming out of the screen, cross means current is entering into the screen, and from here it is coming out. So current out. Now if I take the cross sectional view of this rotor, which is shown here on the screen, cross sectional view, so this side will be dot, this side will be cross, the left side will be the slots carrying dot current, and the right side will be the slots carrying cross current. Now you apply that right hand grip rule, you can plot the magnetic lines of flux. So you can see this is your north pole phase, this thing is your north pole phase, north pole phase, and this thing is your south pole phase. This thing is your south pole phase. South pole phase. Now let us take us to the new diagram. I just repeating this, recapitulating this, the variation of M.M.F over a slot pitch. You can see these are the slots. So this portion is the slot containing 4 conductors. So if I write like this slot is containing, this slot is containing 4 conductors. This slot is containing 4 conductors. isn't it? This slot is containing 4 conductors. Each conductor carries current I. 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 Now we apply, this is a path number 1, 2, 3, you can see it is written here. So you apply Ampere's circuital law in path number 1. So apply Ampere's circuital law for path number 1. Apply Ampere's circuital law. Apply Ampere's circuital law for path 1. For path number 1. What is the net current enclosed? Net current enclosed is 0. For this path, for path 1, net current enclosed is 0. So no M.M.F. For path number 1, for path number 1, net current enclosed is 0. Net current enclosed is 0. Hence M.M.F acting along path 1 is 0. Hence M.M.F acting along path 1 is 0. So that is what is shown. Now in path number 2, what is the net current enclosed? If I again apply the same approach, so you can see in path number 2 the M.M.F acting along will be 2I because the current enclosed is 2I, and likewise in path number 3 it will be 4I, in path number 3 4I, but in path number 4 also it is 4I. So what do you see? That no variation of M.M.F over the tooth portion. So this is your tooth portion. This thing is, this particular thing is your tooth surface. This is the surface of tooth. This thing is the tooth surface. This thing is your tooth surface, and this portion is the slot. This portion is the slot. So you see no M.M.F variation over tooth portion. So if I write like this, you can see no M.M.F variation, over tooth surface, So that's why it is parallel. Now this is the actual variation, but approximate variation is shown like this. So you can see the change in M.M.F over a slot is indicated at the middle of the slot. So this is an important point. I would like you to notice it, is that change in M.M.F over a slot portion, change in M.M.F over a slot portion, change in M.M.F over a slot portion is indicated at the middle of the slot, middle portion of the slot. So the actual nature of M.M.F variation over a slot is smoothly rising over the slot portion, linearly rising over the slot portion, but we approximate it by a step jump. So this M.M.F nature is actually step jump. This M.M.F nature is like a step jump, is like a step jump, is like a step jump. Step jump. And this M.M.F nature is linearly rising over the slot. This M.M.F nature is linearly rising over the slot portion, is linearly rising over the slot portion, over the slot portion. Over the slot portion. Over the slot portion. So this is an important aspect which you should remember, that actual variation of M.M.F over the slot portion is like this. It is linearly rising over the slot portion. But we don't go by this kind of representation. We actually use the approximate version. The approximate M.M.F variation over the slot pitch is like a step jump. You can see there is a jump in the step. If I just place it like this, you can see there is a step jump. Let me use some color, another color. You can see I am using this green line, so it is indicating the step jump. So this is the step jump, step variation usually, which is used, the approximate one. But actually the variation of M.M.F is linearly rising over the slot portion, which is shown here. But we use the approximate one. Now based on this idea, if you want to plot the variation of M.M.F over the rotor surface, so this is the actual variation of M.M.F over the rotor surface. Okay, so this is the actual variation. So this is you can say it is like trapezoidal variation. So if I write the phrase, the variation of M.M.F over the rotor surface, variation, or let's use the word space distribution, that is also going to have the same meaning. So let me use that only, space distribution of M.M.F, space distribution, space distribution of field M.M.F, over the rotor surface, over the rotor surface. So this is the space distribution of field M.M.F over the rotor surface. It is like trapezoidal. Now how we have actually found out, we have taken some convention. What kind of convention? That if lines of flux are leaving the stator core and entering the rotor core, they will be treated as positive, and vice versa. That means if lines of flux are entering the stator core or leaving the rotor core, they will be treated as negative. So based on this, we have applied Ampere's circuital law and we have plotted the M.M.F variation. You can see whenever you are traversing along any one path, you are actually crossing the air gap twice. So that means what? The drop in M.M.F in air gap is happening twice when you are moving along one path. So if I take this outermost path, so it is enclosing all the 5 conductors, 1, 2, 3, 4, 5. And if the current carried by the conductor is say IF and the number of turns is NF, so the total M.M.F is 5 NF into IF. But this M.M.F, if you consider, you are actually crossing the air gap twice when you are moving along this path. Let me name it. Let me name this portion. Let's say I am naming this as path number 3. This is say path number 3. This is a path number 3. this portion. Fine. So what is the conductors enclosed? 1, 2, 3, 4, 5. So what is the M.M.F? M.M.F has to be your 5 times the number of conductors in each slot. Let's say in each slot there are NF number of conductors. So if I write like that, let's say in each slot there are NF number of conductors and the current carried is IF. So what is the current carried? Is IF. IF is the current carried. Okay. So in each slot there are NF number of conductors. In each slot there are in each slot there are NF number of conductors. NF conductors. NF conductors. In each slot there are NF conductors and current carried by the field winding is IF. Current carried by field winding is IF. Current carried by field winding. Current carried by field winding is IF. Field winding is IF. So what is the current enclosed in this path? Current enclosed in this path will be 5 NF into IF. So the current enclosed by this closed path will be 5 NF into IF. NF into IF is the current enclosed. But if you move along this path, if you are moving along this particular path, you have to keep in mind you are crossing the air gap twice. You are crossing the air gap twice. So the drop in M.M.F will be also twice. Fine. So that's why this height will be 5 by 2 into NF into IF. So this height will be how much? This will be 5 by 2 NF into IF. Because you are crossing the air gap twice. Likewise, you can use this thing. So we have used that convention. Lines of flux leaving the stator core and entering the rotor core are positive. Let me mention here lines of flux, lines of magnetic flux, lines of magnetic flux leaving the stator core, leaving the stator core, leaving the stator core and entering rotor core, and entering rotor core and entering the rotor core, entering the rotor core is treated as positive, is treated as positive and vice versa. So that way we can obtain this kind of M.M.F distribution. Now you see it is trapezoidal in nature. It is far from sinusoidal. But we can apply Fourier series expansion and we can approximate this by a trapezoidal waveform, by a sinusoidal waveform like this. If I, let me plot it. So the actual distribution of M.M.F is like this, trapezoidal, the space distribution of M.M.F. But we can apply Fourier series expansion and so let me do one thing. Let me try to sketch a sine wave which will be termed as the fundamental component. So I am trying to sketch one sine wave which will be termed as the fundamental component. So this is the M.M.F. So what we are calling this we are calling as the fundamental component. This thing is the fundamental component. This thing is the fundamental component. Fundamental component. Fundamental component of M.M.F. Of course, we are talking about field M.M.F. So this is the fundamental component, and of course there will be harmonic components as well. We are not showing the harmonic components. We are not showing the harmonic components. Let me try to indicate one harmonic component. So this can be your harmonic components. Okay, so over here the harmonic components are not indicated. Let me remove the harmonic components. Only fundamental component is shown, and we are neglecting the harmonic components. So obviously, let me mention here, space harmonic components are not indicated. Space harmonic component, space harmonic component of M.M.F. Not indicated. Not indicated. So from henceforth now on we will say that the distribution of magnetic flux density, that is distribution of B magnetic flux density over the rotor surface, will be treated as sinusoidal, because we are only going to take the fundamental component of M.M.F. The space harmonic components won't be taken into consideration. Okay. So once we are clear with this, let us now move to the next portion. Is that this, you can see over here, there is a armature winding on the stator and field winding on the rotor. The usual arrangement which is there, armature winding on the stator, field winding on the rotor. So what you can see that if we are rotating, let us rotate this rotor in the anti-clockwise direction. Okay, so although I have mentioned here this particular thing, I have mentioned, so I would not keep it like that. So I will, let me color this thing. This won't be there. I will take anti-clockwise direction so that you don't have the trouble, because in the book of in your textbook mostly they are showing like that, anti-clockwise direction. So here it was shown in clockwise, so I am making it anti-clockwise. Let me show you. Let's say the rotor is rotating in anti-clockwise direction like this. This is the direction of rotation of the rotor, anti-clockwise. So what is the induced EMF polarity in these coils? So how to find it? So we will draw the rotor. This is just for your explanation. So what you are having basically, let me use some another color, otherwise let's say I am drawing the rotor and I am having, say, north pole over here, I am having, say, south pole over here, and these are the conductors. This 1, 2, 3, 1, 2, 3. So these are your dot current, these are your dot current, dot current, dot current, dot current, and these are your cross currents. Now, what is the direction of B? B means the magnetic flux density due to current carried by the field winding. Inside the magnet, lines of flux are from south to north. So this is the direction of magnetic field created by the rotor BF. Now, what you will assume that the rotor is stationary and coil side A is moving in opposite direction. Let me show you. This is the peripheral speed of the rotor surface. If I draw like this is the peripheral speed for the rotor surface. This is the peripheral speed. This is the peripheral speed of rotor surface. Of rotor surface in front of coil side A. In front of coil side A. In front of coil side A. So what you will do, you will assume that rotor is stationary. Assume that rotor is stationary and coil side A is moving in opposite direction. Opposite direction. Assume that rotor is stationary and coil side A is moving in opposite direction. Opposite direction means opposite to peripheral speed of rotor surface. Opposite to peripheral speed. Opposite to peripheral speed of rotor surface. So that means we have to assume that conductor A is going to move in this particular direction. Let me change the color. This is what we are assuming. Okay. So now let us apply Fleming's right hand rule. Let us apply Fleming's right hand rule. Let us apply Fleming's right hand rule in order to find the induced M.M.F polarity. In order to find induced EMF polarity, induced EMF polarity for coil side A. So we will place the direction of motion of the conductor and magnetic field, all those things. So let us find out that. So what is the direction of motion? This is your V, direction of motion. What is your B? This is your direction of magnetic field B. So what you will do, this is right hand index finger. This thing is your right hand index finger. Right hand index finger. Right hand index finger. This thing is right hand thumb. This thing is right hand thumb. Right hand thumb. So you align this way. Align the right hand index finger and right hand thumb. Right hand thumb along the velocity vector v, and right hand index finger along the direction of magnetic lines of flux. So the middle finger will point out of the screen. So we can say that this middle finger will point out of the screen. This thing is 90 degree, this thing is again 90 degree. So this middle finger points out of the screen. Right hand middle finger, this is your right hand middle finger. Right hand middle finger pointing out of screen. Pointing out of screen. So pointing out of screen means that it is your dot polarity. This thing is your dot polarity. So this will be dot. Induced EMF polarity will be dot. This will be dot. Now, north pole surface is this one. Let me sketch it. This thing is your north pole surface. And this thing is your south pole surface. So this thing is your south pole surface, south pole face. This thing is your south pole face. And this thing is your north pole face. North face, north pole face. This thing is your north pole face. You can plot the lines of flux if you wish. You can see these will be the lines of flux. I am plotting few of them, not all of them. So you can see the direction of the lines of flux. You can see the direction of the lines of flux like this. Okay. Now, so coil side B dash C dash under north pole face, so they will also have dot. They will also have dot polarity of induced EMF. So this will be dot. This will be dot. Dot. This will be also dot. And under south pole it will be opposite. It will be cross, cross, cross. So you have to notice this particular point very meticulously, that under south pole face, let me write coil side C A dash B. Coil side C, coil side A dash, coil side C, A dash and B, coil side B. Coil side B. They are under the influence of south pole, are under influence of south pole. Influence of south pole. Likewise, you can see coil side B dash, A and C dash, they are under the influence of North Pole. So we can write coil side B dash, A and C dash are under influence of North Pole. Are under influence of North Pole. Influence of North Pole. Influence of North Pole. So that is the reason we have put up the dot polarity of induced EMF for coil side B dash and C dash as well. Although we have found out for coil side A, but we have mentioned that for coil side B dash and C dash also, the induced EMF polarity will be dot only, because all these three coil sides B dash, A, C dash, they are under the influence of North Pole. Now if under North Pole it is dot, obviously under South Pole it will be cross. Nevertheless, you can still apply the Fleming's right hand rule, but you have to be careful. You have to apply the Fleming's right hand rule in a modified way. You cannot apply directly, because here the field is itself moving. The field is on the rotor. Rotor is moving, so magnetic field is moving. And the coil side of the conductor in which EMF is to be induced, they are stationary because they are in the stator. So that is the reason we have to apply Fleming's right hand rule, but in a modified way. You have to assume that rotor is stationary and coil side is moving in a direction opposite to the peripheral speed of the rotor surface. So that way you can apply that Fleming's right hand rule. So I am keeping up to this point only.